Let me show you one of the most important proof for Ito's calculus, which is quadratic variation. Notation first, Brownian motion. We can calculate the sum of Brownian motion one time slice minus the time slice before square. This can be pretty much similar to like a dBt squared. For this, minus this squared can be considered as essentially a two very infinitesimally small time slice. And essentially this minus this as a based on the definition of Brownian motion, the distribution of this is essentially a normal distribution with standard deviation of the standard deviation square of t over n. Thus, the expectation value of this will be t over n. Since we're gonna sum over n times, so n multiplied t minus t over n. Thus, we have t. We have dBt squared equals dt. This is very interesting because you in normal smooth function, you can imagine is much smaller than this, much smaller than dt. But for a Brownian motion, it is not the case. Thus, it's not a smooth function. For me, intuitively speaking, I can imagine the bt squared. If you take the bt square of its expectation, it's always will be like a straight line like that. Because you're just gonna either go. You can think of like a binomial. This binomial, you flip a coin, go up or down. This can be described with Brownian motion. Thus, we go up and down. The absolute value is always the same, +1 -1. Then you always is absolute value is always 1. You go 1 and 1. Thus, the dBt square is dt. It is a t. Thus, we have dBt squared equals dt.